Assalamu alaikum. How are you, my dear students? Hope you will be in the best of health, wealth, and happiness. I welcome you all into my today lecture. Today is our 25th lecture, Unit 14, Electromagnetic Induction. And our today topics are mutual induction and AD current. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. The first topic is the AD current. Oh, sorry, the mutual induction. Mutual induction. Now, what is mutual induction? It is defined as it is the it is it is the process of it is the process of generating induced EMF or current induced EMF in one coil. In one coil, we call that coil as the primary coil. In one coil, due to the change of current, in another nearby coil, that coil we call the secondary coil. Is called what? Is called the phenomena of mutual induction. Mutual induction. If you remember in the previous lecture, I told you that it is the changing magnetic flux in the nearby region of a conductor which is the cause of the induced current in that conductor. And then I told you that changing magnetic flux can be achieved by using the changing current also. This induced current in the secondary coil, though maybe the subscript use your book is not matching with mine, but I think that is not a good way they have dealt things. So this would be the better for you if you follow. This secondary induced EMF is equal to the mutual induction times the rate of change of the rate of change of current in the primary circuit, delta P by delta T, delta AP by delta T. Let me derive this for you. That is, this induced EMF in the secondary coil is the mutual inductance times the change of current in the primary coil. Now let us see that the coil here you see where there are N1 number of turns, and better I would label it as NP number of turns, and this NS number of turns, and this pi I would write pi S, the flux in the secondary. So this one is our primary coil. This is primary, right? Why? Because it is connected across the source of changing current, maybe AC like this, or it may be a variable resistance with a battery. Here you do not have the source. Here you will see the induced circuit, the induced current. Let's say for example in this is flowing in this direction, right? And this is I, the induced current. Here it will be indicated by the galvanometer, like this one. Now you see that whenever there is change of current in the primary coil, then the magnetic field in the primary B, it changes, right? This change of magnetic field will cause a changing magnetic flux in the nearby region of this secondary coil. Some of the line pass through the secondary coil and will become the cause of the induced current in the secondary coil. Now, look, that experiment shows that, let me copy it here. See here. Now, look, experiment shows that the flux that changes this, as I already told, that better to write this as n as number of turns in the secondary, and this is psi s, because this is our secondary coil, if you remember. Okay, so now you see, look, experiment shows that the change of flux in the secondary is directly proportional to the rate of change of current in the primary coil. As I told to you, that this is the current in the primary. So look, remember, we do not need the steady current or the constant current. This will be a changing current, right? So if there are more than one turns in the secondary, then this will the flux through the secondary will increase by what? By n times, because if we increase the number of loop in this. So this is our equation number one. Or let me write here like this, that this n into delta pi s flux through the secondary coil is equal m into delta ip. Now, what is this M? This M is called the mutual inductance of the circuit. The mutual constant of proportionality, and is called the mutual inductance, right? And this mutual inductance of the circuit, this mutual inductance of the circuit, it depends on few important things, right? First, this purely depends on the geometric properties of the coil. For example, the first thing on which it depends is the product or the number of turns in both of the coil. Remember, it's not on one. Number of turns in both the coils. In both the coils, it depends on this. Depends on the area of cross section of the coil. Area of cross section of the coils. It depends on this. C, it depends on closeness together. Closeness together. That is the minimum or the smallest distance between the two coils, right? This distance, you see, look, this is closeness together, this distance, let's say d. So the smaller this distance, the greater will be the mutual inductance. And next is the d number. The next one is the d. And d, that is the nature of the core material. Nature of the core material, that is the permeability of the free space. Now it depends that whether there is air, or if there is medium other than the air. For example, if there is medium other than the air, like for example, the iron bar, the soft iron bar like this, then what will happen? This will increase the mutual inductance. If you connect the two coils with the help of what? With the help of soft iron bar, then the soft iron bar is best. This is the core material, the core material. And this core material is best in linking magnetic flux, in linking the magnetic flux, the magnetic flux from the secondary coil, that is secondary coil, and this is what the primary coil, as you see. So that is the it depends on the nature of the core material also. Soft iron core is the best for this purpose. Soft iron core, right? That is best in linking the magnetic flux. So here this I will label as my equation number 1. Now from Faraday law, now from the Faraday law, what does the Faraday law tell us? Faraday law. And the Faraday law states that the induced EMF in the secondary coil is directly proportional to the rate of change of flux through the secondary coil. This is the delta pi s into delta t is the rate of change of flux through the secondary. Now, if there are n number of turns in the secondary, it will be ns into delta pi s by delta t. And I will add one negative sign. The negative sign indicates the direction of the induced current or the induced EMF polarity. Now, this can be rewritten as ns into delta psi s. I will write it like this, minus this into ns, where this is the EMF in the secondary coil. So this is our equation number 2. So from 1 and 2, we can write that minus this psi s into epsilon s into ns. Sorry, yes, it will be equal to, no, I'm very sorry, very sorry. This is delta t. Look, here it is divided, there it will be multiplied, right? So the equation will now reduce to, if we use 1 and 2, then it will be like this, delta t into m delta ip, and we will write that the induced EMF in the secondary is the mutual inductance times the rate of change of current in the primary. And what in the primary, that is delta t, right? Where M is called the mutual inductance, and this M can be found as like this by delta I by delta T. And same, the SI unit again here is also Henry, and 1 Henry is equal to volt second per ampere. So the mutual inductance is said to be 1 ampere if a current, 1 Henry, if a current of induced current of 1 ampere is, yeah, if the, let me tell you it in the most easy way. The mutual inductance is said to be 1 Henry if a rate of change of current of 1 ampere per second cause in EMF of 1 volt in the secondary coil, then the mutual inductance of the coil is said to be 1 Henry. All the factors I told, that what are the possible factors. Here the negative sign indicates that it is what, that the it indicates the direction of the induced EMF. Here your book version goes here according to your book. they says that the induced EMF in the secondary coil is directly proportional to the rate of change of current, but they are not mentioning that how, where, because there is induced current also. So we should specify that the rate of change of current in the primary circuit, or then they write that this induced EMF in the secondary is equal to M into delta I by delta T, right? This is what, this is the required equation which we have derived here. Another important point which I want to tell you is this one, that you must remember the equation N pi into Mi, just like N pi is equal to Li. So this is also an important equation which we will use down the road. The next our next topic is the AD current, and that is also a very important topic, right? Because it has many application. Better you study this by yourself, but let me do this for you. The AD current, that what is AD current? The AD current. AD current is the induced current. What the, it is also in the same way that it is what, it is the induced current, the induced current caused by changing magnetic flux, caused by what, by changing magnetic flux, magnetic flux in the nearby region, in the nearby region of a metal piece or conductor. The metal piece or a conductor. Now you see that here there is one difference here, that of the proper induced EMF in the AD current, and that difference is that this AD current, that it is, whether it intend or not, it has to be produced. What, whether intend or not, if you want it or if you don't want it, doesn't make any difference, whether intend or not, intended or not intended. Okay, it doesn't make, your choice is not here. Why? Because that it is all natural. What, this is all natural. This is the intrinsic property of the changing magnetic flux, that it would induce EMF whenever it is in the nearby region of a conductor or coil. So this is what, this is this does not depends on our desire or wish, but it has many applications also, and I would like to write the merits also and of the demerits also, demerits also, the unwanted or the undesirable effect also. The merits are, first let me tell you about the production of the AD current. For example, look, if this is, you see here, there is, this is a metal sheet, and when there is a changing magnetic flux, as you see, for example, either the, if the sheet moves across the magnetic field, or if the magnet is moving, then it will produce the induced current in this sheet, right? That induced current will then generate heat energy, R1, or there will be produce a force because of this induced current that would resist the motion of this metallic sheet inside the magnetic field, and it will also produce excess heat energy, because you know power is equal to I square R. So if you have the current, the metal definitely has resistance, and there will be definitely power dissipation, as you see here. So now look how it can be produced. For example, look, if there is we can produce this either by the AD current can be produced by the changing magnetic field of the permanent magnet, as I did it here, okay, right now, or it might be because of what, the changing current through the solenoid. For example, if your solenoid is connected with the AC source, changing AC, alternating current, right, then there will be what, there will be changing magnetic field, and that changing magnetic field would cause current in the metal piece, and that current is called the AD current, right? And there will produce, this will produce a secondary magnetic field. Why? Because there is induced current, and induced current would cause a secondary magnetic field which would oppose the primary magnetic field, right? And then there is what, look, this effect can be used, right, in many applications. As I told you, in some of the case it produce unwanted effect. For example, where it can reduce unwanted effect, its unwanted effect are demerit, the unwanted effect are demerit, unwanted or desirable effect. Desirable effect, that is in the core of the transformer. The AD current in the core of the transformer produces what? Excess heat energy, right? And it is because of the current, that is induced current that flows through the core of the transformer because of this effect. And the second important point here is the merits or the application. Here you see that it can be best used in the metal detector. Here you see, look, for example, when you pass through the scanner, it can detect the presence of the metal by using transmitter coil to create an oscillating magnetic primary magnetic field. Here you see there is a coil. This coil is called the primary coil, and it is called the transmitting coil in the engineering of the this scanner. Now what does this do? There is a changing current that exist in the transmitting coil. If someone pass through the scanner, and if he or she carry the any metals, like for example a knife or anything which can cause danger or which can be used for any other illegal purposes, right, then what will happen? This will create a secondary magnetic field due to AD current in the metal. For example, if here, if you have the metal piece in your briefcase right now, then what will happen, that this will cause what, a second, the induced EMF, and this induced EMF will turn reduce secondary magnetic field or induced magnetic field. And then there is a receiver coil, and it would cause a secondary induced EMF in the receiver coil, right? And that is, it is then connected with a sensor like alarm or light or whatsoever, and it will indicate the presence of the metal piece or like knife or like any other prohibited metals, and the security personnel may easily pick the required person. Similarly, the same procedure is here also used in the detection of the coins, right? To discover the coins underground or the buried by using the metal detector. And here you see, for example, look, there is the magnetic field of the coil. This is the transmitting coil, okay? Transmitting coil, and the transmitting coil will cause to produce induced current in the metal piece. So in turn, when there is produced current in the metal piece, the AD current, it has its own induced magnetic field, and when that induced magnetic field pass through the coil, that coil is called the receiver, right? And then the receiver coil is connected with either this sound system or any other sensor, for example a sound system or a sensor, and it will start sounding, right? Tune tune kind of sound you will hear. So this is all about what, this is all about the AD current. So in our today topics includes what, the mutual induction in the AD current. So hope you might have got the idea of the mutual inductance, that it is the process of generating induced EMF in one coil due to the rate of change of current in another coil. So this is a very easiest way of transferring power from one coil into another without any physical touch, as you see, without any physical touch, right? They are only closer to the nearest possible distance without any physical contact or touch. Okay, this is the best, like just in the same way your cardless charger. So your cardless charger works on the principle of mutual induction. The transformer works on the principle of mutual induction, and this phenomena of mutual induction is implied in what? It is employed in the transmission of power. What? In the transmission of power over a longer distance, right? So inshallah we will learn this in the transformer. So this is our today lecture, and thank you very much for being here. Inshallah, see you in the next lecture.